Hello everyone, and welcome to our video on the formal definition of the limit. So we're going to start by going over the formal definition of the limit, but before we do that, I just want to remind everybody about how we should be thinking about the absolute value bars in this notation. So remember, when we write the absolute value of a, this means the distance from a to 0. And if I write the absolute value of x minus a, this means the distance from x to a. So in other words, if I'm looking at a number line, and here's a and here's x, this distance here is the absolute value of x minus a. So make sure when we go through this definition that you're thinking about these absolute value symbols as meaning the distance here. Okay, so the formal definition of the limit says, we say that the limit as x approaches c of f of x is L if for any epsilon greater than 0, there exists a corresponding delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus c is positive and less than delta. Okay, so a couple details here before we try to break this down and understand what it means. So when we talk about the limit, as we discussed before, we're not talking about the value of the function at the point. So when I look at x approaching c, I don't want x to actually be equal to c, and that's why in the second inequality, it says that this absolute value of x minus c has to be greater than 0, so that x isn't actually the same number as c. So that's just a little thing there. So let's go back through this. What this says is the distance between the f of x value, the y value of the function, and the value of the limit, the distance from the function to the value of the limit, is less than some number epsilon. And epsilon, this is just some number. And it's probably small. I'll illustrate what I mean by that momentarily, but it's just some number, so don't overthink epsilon. It's just a placeholder we're putting in place of some number. So we're saying that when the distance, or that the distance from f of x to L is less than some small number whenever the distance from x to c is less than another small number that we call delta. So again, delta is some number. So if we think back to the intuitive definition of the limit, the intuitive definition of the limit says, for a close enough value of x, the y value gets arbitrarily close to L. That's all we're doing here, is putting that into formal language so that we have more precise tools to work with here. So what we're saying is, for any small number, no matter how small I make it, any epsilon, I can find a delta such that my output of the function will be as close to L as I want. That being epsilon is how close I want the output to be to L. Then the input value, or that will happen whenever the input value is close enough to c. So let's look at this in this picture, right? So we've got a function here. It has a hole at this point when x is c. So the function doesn't actually take any value here. But what we see is when we draw this epsilon here, that if I chart this over and I say, well, look at all of the y values, all of the f of x values that are within this distance of epsilon, all of them land somewhere here for the curve of this function, right? So somewhere in this part of the function. Let me switch that to cursor so it's a little easier to see. So somewhere in here, any f of x value lands in here on the curve. And so what that means is that the x values that correspond to those f of x values are also landing here between delta, between these distances of delta away from c. So the key here to this definition is that it says that this is true for any epsilon. meaning that I can make epsilon smaller and smaller and smaller, and I will still be able to find a delta. I will still be able to find a distance from C that's good enough. So let me illustrate. So let's say I pick a second epsilon here. We'll call it epsilon-2. So it's just this smaller distance. So if I just draw my little lines over here just to keep track of those y values, I end up here. And here. And so what this says is, if I want my y value to be within this distance from the limit L, as long as I pick an x value that's within this new distance here, it'll work, all right? So this new distance we'll call delta 2. And if I pick a smaller epsilon, if the limit exists, I can find a smaller delta that'll still keep me in that range when all of those x values on the graph will correspond to those same y values. So hopefully that makes some amount of sense. Let's go ahead and take a look at an example here. So we're going to use the graph below to complete the following statements. So here we've got the distance from f of x to 3 is less than 0.2 whenever the distance from x to 2 is less than what? So I'm going to look at the y-axis here, right? This is f of x, so we're looking at the y-axis. And we'll look right here. So this is 3. And I want to go out a distance of 0.2 in each direction. Now, if we look at this graph, it goes up in 5 segments for every 1, right? From 3 to 4, there's 5 segments. That means each of those segments is 0.2. So I'm just going to go up to the distance 0.2 away from 3 and go across here and mark my graph. And then I'm going to go 0.3 or 0.2 down. I'm going to do the same thing. So I'm just doing this to mark my graph so I can see where on the graph those y values correspond to. And now I want to figure out, okay, well, which x values correspond to this part of the graph. So I'll just draw my dotted line down here so I can keep track of where I am. Now, I've got 2 different distances here on my graph. And we need to pick a delta that works on both sides of this number 2, right? So this is the number 2. So I need to pick one delta that makes sure that the x values here correspond to y values on the graph here. So I always pick the smallest delta, because if I pick the biggest one, then if I go out too far on one side, I don't get a point on that part of the graph anymore. So I pick the smallest of these 2 distances. So if I just kind of zoom in here, it's not great, but we can figure out roughly what this distance is. What's this delta? Well, here, notice on the x-axis, the graph is split up a little differently. The x-axis is segmented into 4 pieces for each number. So that means if I go out this distance, that's 0.25, right? So delta is approximately 0.25. So I'll put 0.25 here. Now I'm going to repeat the same thing. But now we're going to look at the distance between f of x and 3 being less than 0.1. So now, if I look back here at 3, if I only want to go out 0.1, that's half as far. So I go out half as far, and I'm going to do the same thing. I'm going to draw my little dotted line, mark my graph. So now I'm trying to figure out what x values correspond to just this part of the graph. But again, in terms of the distance away from 2 that those x values are. So we scroll back on down, and we're going to carry these dotted lines through. Okay, so this one, I'm going to have to erase some of my previous marks just to make it a little easier for you to see. All right. So we'll just go ahead and erase that. Sorry, you may have to rewind the video if you need to see it again. So now we're just looking at this part of the graph. Okay, so I want to figure out roughly what's this distance away from 2. And again, I look at the two sides and I look at the shorter distance. This side on the left is a little further out, so I pick the shorter distance. And I got to estimate that. Well, that's about halfway through one of these little subdivisions. So if this is 2.25, I would call, this distance is 0.5 for a whole square, or 0.25, I mean. Sorry about that. Then for half of that distance, it should be roughly 0.125. So my delta should be approximately that. And for this type of problem, anything in a reasonable ballpark is fine, right? If you said 0.1, I'd be like, yeah, that looks roughly about like 0.1. I'm totally happy with that. So hopefully this helps emphasize the idea here, that all we're saying is that we can pick for any epsilon, no matter how small the distance you make between the function value and the limit value, you can find a delta where the x values within that range are going to correspond to that part of the graph. Now, one little thing I want to add before we move on is just a little clarification on wording here. So you will see the definition of the limit worded in two slightly different ways, but they're both equivalent. So here we've said, for any epsilon greater than 0, there is a corresponding delta greater than 0, such that when the distance between f of x and L is less than epsilon, whenever the distance from x to c is less than delta. So this part I've written in green here. Another way of saying this is if the absolute value of x minus c, I should say, is positive. If the absolute value of x minus c is positive and less than delta, then the absolute value of f of x minus L is less than epsilon. So I want to be kind of clear where the cause and effect is here, right? It's what we're saying is that if I pick an x value close enough to c, close enough being whatever this distance delta is, then I will get a y value close enough to epsilon. So if I pick an x value that's within this distance from c, then I'll get a y value within that epsilon distance from L. Okay, so we've kind of harped on the definition long enough. Let's move on to actually applying these ideas. So example 2, and I've called this a motivating problem because it's an application problem that should hopefully help you see that this formal definition of the limit isn't just some like arbitrary complicated thing that we've done just to make things harder than it needs to be, but actually these are important ways of accurately describing the ideas that tie to real-world applications. So it's not just like an esoteric thing, it's actually how we think about applying these concepts in the real world. So let's take a look at this problem. A certain motor is used to pull a cable which is attached to a gondola. So that's a cable car. So I mean something like this. You got a cable, there's like a car with like a motor on top. It's got maybe a door here. If you've ever been in a theme park, there's a good chance you've seen something like this. So the length of cable it pulls is given by f of t equals 5t feet, where t is the number of seconds since the motor has been turned on. So in other words, if t is 3, meaning if you leave the motor on for 3 seconds, this motor will pull the car 15 feet, right? So the operator needs to stop the motor once it pulls about 100 feet of cable. Within what time frame must the operator turn off the motor to ensure that the amount of cable pulled is within 2 feet of the 100 feet needed? And then to add on to this, in terms of the formal definition of the limit, what is x? What is f of x? What is a? What is L? what value of epsilon is given and what is the corresponding value of delta. Okay, so let's start with what we're given. We're given that the function, the motor, pulls the cable at 5 feet per second, and we want, ideally, to pull a total of 100 feet of cable. So in other words, we want the absolute value of 5t minus 100 to be less than an error of 2 feet, right? It says we want to assure that the amount of cable pulled is within 2 feet of the 100 feet needed. So this might mean that, hey, there's a little platform here, and there's a little overhang 2 feet in each direction, and so you need to make sure that you're within at least that 2 feet of extra overhang when you stop the cable car. So we want the distance between 5t and 100 to be less than 2 feet. Now we want to try to figure out what time frame the operator would need to turn off the motor to get to that particular range. So now let's keep in mind, what is our ideal, right? What is the ideal moment that the cable car operator will stop the car? Well, we'd be even happier if 5t was 100, right? That would be like the ideal, if they could stop it at the instant. But hey, we're human beings, so that's not super realistic. But if that happened, then t would be 20, right? So let's keep that in the back of our head. Now, I want to figure out some way to solve for t here using this inequality. And the first thing I realize is I can factor out a 5, get 5 times t minus 20. Absolute value is less than 2. And I can split up that absolute value on the product. And now I just divide by the 5. The absolute value of 5 is 5. So this becomes the absolute value of t minus 20 is less than 2/5. So that's kind of nice because now... Oh, 1 second, there we go. Now I can split up my absolute value. So this is the same type of algebra we dealt with in our review on inequalities involving absolute values. So we split up this inequality to be between negative 2/5 and positive 2/5. And now I'll add 20 to both sides. So this is 20 and 2/5, which is the same thing as 20.4. And this is 20 minus 2/5, which is the same thing as 19.6. So this is the range of time where the operator would need to shut off the car. So we see basically the operator has about a 0.4 second leeway in either direction, right? Okay, so now let's tie this to the definition of the limit. So in terms of the formal definition of the limit, what is x? Well, here, x is t, which is the number of seconds the motor has ran. Right? Because look here, we've got the absolute value of t minus 20. This is like the absolute value of x minus a is less than delta, right? And what is f of x? Well, f of x is really a function of t in this particular example. And this function is the amount of cable pulled by the motor over t seconds. Okay, what is A? Well, A is the ideal stopping time. And notice that the ideal stopping time was 20, which is exactly what we get here, t minus 20, just like our x minus a form for the definition. And in particular, we should specify the value a is 20 here. What is L? Well, L is the ideal length of cable pulled. And in this case, that's 100, right? So if we look up here, this is the absolute value of 5t minus 100. That's our f of x minus L is less than epsilon, right? So what value of epsilon is given? Well, the value of epsilon that was given was 2. And what is the corresponding value of delta? We'll look over here. That's 2/5. Okay. So hopefully that helps make this definition of the limit make a little bit more sense when we look at it in terms of a real-world problem. All right, let's move along and take a look at another application problem. This one's going to have something a little bit tricky in it. So one thing I want to point out that was really nice about the previous problem was that the function we had when we set up our f of x minus L inequality, we were able to factor it in such a way that we could get t minus a inside the absolute value. So we could explicitly solve for delta in this case. That's not always possible. And so we're going to take a look here at this example where it isn't possible and see how these tools are still useful in that case. So a certain manufacturing process produces steel billets, the rectangular prisms made of steel in the shape pictured below. So it's just like a rectangular prism. That's all it is. Whose volume is given by V equals 2x cubed. And so what that means is one of your dimensions of this billet is twice as long as the others. However, there's always some variation in the product's dimensions. If the manufacturer wants to guarantee that the volume of a billet with volume 2,000, or I should say with ideal volume, 2,000 inches cubed is accurate to within 1/10 of an inch cubed, what is the maximum deviation allowable in the dimension x? So this is delta. In other words, it's asking us to solve for delta here. How far away from the ideal x value can we be? Well, in order to figure that out, first we're going to need to know what is the ideal x value. So we would like 2x cubed to be equal to 2,000, but that implies x cubed is 1,000. Which implies x is 10, the cubed root. So I wrote x here, but really we're talking about the ideal, so let's put it in the notation that we use for limits and call this a. So in other words, our ideal value for x, a, is 10, right? That's the ideal dimension. Or sometimes we also call it the target value of x. Okay, so that's our target value for x. Now, what do we know? We know what the actual volume is, right? 2x cubed, the formula, depending on the value of x. And we know we want it to be close to 2,000 inches cubed. And how close? Well, we specified within 1/10 of an inch cubed. Okay, so now we have to try to figure out how to solve for this. Absolute value of x minus 10 is less than delta. The delta is what we want. The problem is I'm not going to be able to rewrite this inequality in this form because there's nothing I can do to get rid of the cubed root as it is, right? If you try to take the cubed root of the whole thing, you can't simplify this because you can't split up a cubed root on a difference. So that won't help us any. So instead, we're going to first start by solving this inequality explicitly. So we do that the same old way. We split the inequality into the positive and negative portions. Now I'm going to add 2,000 to each side. So we get 2x cubed is less than 2,000 plus a tenth. That's 2,000.1. And greater than 2,000 minus a tenth. That's 1999.9. Okay, so far so good. Now I'm going to divide everything by 2. So I get x cubed is greater than. And for that left side, I get 999.95. And for the right side, I get 1,000.05. Okay, now I'm going to solve this by taking the cubed root of each part of the inequality. So we get the cubed root of 999.95, I should say. Is less than, x is less than the cubed root of 1,000.05. And if we were to plug that into a calculator, we get that x is between roughly 9.99983 and 10.0007. Now we get kind of lucky here that this function is a cubed root. It has nice symmetry. So we see that x goes out a distance that's the same in each direction. What do I mean there? I mean, if we go to actually check our absolute value of x minus a, which is x minus 10, right? What's the worst case scenario? Well, the worst case scenario for x is either endpoint here. So we can have x could be almost, I mean, it is strictly less than this number, but it could be almost 10.00017. And so if I do that minus 10 and take the absolute value, I get 0.00017. And I can also look at the other endpoint, 9.99983 minus 10. If I take that absolute value, I get the absolute value of negative 0.00017, which is positive 0.00017. So I actually get the same value for both of these when I check the absolute value of x minus a. But normally, that won't happen. That just happens to be because this function is a cubic function, so it's got some nice symmetry on either side, but that's coincidental. In general, just keep in mind that if you are checking for delta this way, delta would be the smallest value, right? You always want to basically take the worst case scenario. Okay. So you can see that we might get lucky and be able to do some nice algebra and explicitly solve for this delta, like we had in this previous problem. Or maybe we have to solve for our inequality first to solve for the range of x values, and then check the endpoints of that interval to see what the smallest value would be to find out what we should set delta to be. Okay. Example 4. All right, so now we're going to get to the more pure math side of this. Use the definition of the limit to show that the limit as x approaches 3 of 4x minus 2 is equal to 10. Now, the definition of the limit says for any epsilon. So we can't pick a particular epsilon when we're actually proving that a limit has a certain value. We have to show this true no matter what epsilon value we had involved. So that's a really critical part here. So let epsilon greater than 0 be given. We usually start with this to say, hey, it doesn't matter what epsilon you give me, I'm going to be able to work with it. So give me whatever epsilon you want, right? Give me any number epsilon and I'm going to show that this inequality for our definition works. So what we want to show is that the absolute value of x minus a, being less than delta and positive, implies that the absolute value of f of x minus L will be less than epsilon. Okay, so let's look at the particular function we've got here. This is our function f of x. L is 10. So we know that for x minus 2, minus 10 needs to be less than epsilon. So now we're going to use a particularly useful symbol here. So we've been using the implication symbol a lot. That means therefore. So many students will misinterpret this symbol, but remember this double bar arrow means therefore or implies. But we're going to start using a new symbol. That's the double bar arrow in each direction. So this symbol says, so if I write a statement P and another statement Q, it says P is true if and only if Q is true, meaning that both statements are completely equivalent. So for example, I might say x plus 1 is 2 if and only if x equals 1, right? That's both of these statements are true. If either of them is true, the other one is true. If x is 1, then x plus 1 will be 2. And if x plus 1 is 2, then x will be 1, right? So just a little notation clarification here as an aside. Okay, so back to the problem. So because the logic of the formal definition of the limit says if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. We need the inequality to go both ways if we're going to start by working with the conclusion. And so we can say here that, yeah, it's true if and only if the absolute value of 4x minus 12 is less than epsilon. Those are equivalent statements because negative 2 minus 10 is negative 12, period. So now my goal here is to figure out what delta should be, because the definition says if epsilon is given, then I can pick a delta to make this inequality work out, right? So that means I have to try to rewrite this to somehow get the absolute value of x minus a. And so I know that this statement is also true if I factor out the 4 and I put the absolute value of 4 times the absolute value of x minus 3 is less than epsilon. So that's another if and only if statement. And this is also equivalent to taking the absolute value of x minus 3 is less than epsilon over 4. So that looks like my absolute value of x minus 3 is less than delta. So this is what I pick for delta. So now to wrap this up, we can say choose delta equal to epsilon over 4, then the absolute value of x minus 3 being less than delta, which is epsilon over 4, will imply that the absolute value of 4x minus 2 minus 10 is less than epsilon, which implies the limit is 10 by definition. Okay, so we used if and only if statements to work out from the absolute value of f of x minus L being less than epsilon how we should have picked delta to make this true. And since they were if and only if statements, that means the implications go both directions. So that tells us, hey, we've already done this work here. So now we know if the absolute value of x minus 3 is less than delta, which was chosen to be epsilon over 4, then I'm going to get that my f of x minus L's absolute value is less than epsilon. All right, so let's go ahead and move on to another example. So this one's a little bit different, and it's seemingly more complicated. It says, use the definition of the limit to show that the limit as x approaches 3 of x squared minus 9 over 2x minus 6 is 3. So again, we start by saying let epsilon greater than 0 be given. Doesn't matter what it is, just that it's positive. Then if we look at the function, so the absolute value of f of x minus L is x squared minus 9 over 2x minus 6 minus 3. If this is less than epsilon, what else can we say? Well, this is true if and only if the absolute value of x minus 3 times x plus 3 over 2 times x minus 3 is less than epsilon. Because it's the same statement, right? All I did was factor those expressions. Now this is true if and only if the absolute value of x plus 3 over 2 minus 3 is less than epsilon. And notice all I did here was cancel these matching factors. Now, if x was equal to 3, I can't do that canceling, right? Because I would be dividing by 0. But remember, we're talking about a limit here, and the definition of the limit assumes that x is not 3, since that's the value we're approaching. That should say x is not equal to 3. Okay, so my goal remains the same, right? I want to figure out what delta is, so I want the absolute value of x minus 3 less than delta. And so here I've got x over 2 plus 3 over 2 minus 3 is less than epsilon. If I factored out a 1/2, that would at least let me isolate the x. So I factor out a 1/2, and what do we get left? We get x plus 3 minus, this is a little tricky, because how do you factor out a 3, 1/2 out of 3? Well, you have to double the number, right? So if you're ever tripped up on factoring things like that, remember, if you redistribute, you should get the same thing you started with. And so I can say, what number multiplied by 1/2 gives me -3? The number is -6, right? And so this becomes 1/2 times the absolute value of x minus 3, right? Plus 3 minus 3. And this is still less than epsilon. And this is true if and only if the absolute value of x minus 3 is less than 2 epsilon. So this is what I should pick my delta to be. Right? I've got the absolute value of x minus 3. The distance between x and 3 is less than delta. So we say choose delta equal to 2 epsilon. Then if we've shown that if the absolute value of x minus 3 is less than delta, which is 2 epsilon, that will imply that the absolute value of x squared minus 9 over 2x minus 6 minus 3 is less than epsilon. Therefore, the limit as x approaches 3 of x squared minus 9 over 2x minus 6 is 3. By definition. So hopefully what we see in this one is that this example was super similar to the first example we did like this. The only difference was we had to factor and cancel first. Now we're going to look at a squared function that we cannot factor and cancel first. Well, we can factor, but we can't cancel. What do I mean? Well, we want to use the definition of limit to show that the limit as x approaches 5 of x squared is less than 25. So we start out by let epsilon greater than 0 be given. And now we look at the absolute value of f of x minus L, x squared minus 25, less than epsilon. Well, how am I going to work with this? Because remember, the goal is to reach this expression. The absolute value of x minus a is less than delta, so I can figure out what delta would need to be. How do I reach that goal? Well, I start by factoring this x squared minus 25, which factors to x minus 5 times x plus 5. And that's going to be less than epsilon for sure. So now we're going to do another little aside here. Since we're talking about a limit, so since x is approaching 5, we can assume it's close to 5. Because we don't care what's happening like when x is 1,000, right? When we're talking about a limit, we're caring about what's happening right near 5. And we can kind of pick how near we want to look at when we're thinking about these limits. So I'll choose to assume that x is between 4 and 6. Now, I want to be clear. You could assume a smaller interval, right? You could make x between 4.9 and 5.1 if you want. I just picked easy numbers, right? But what we know is that x is going to be close to 5, and it can be as close to 5 as I want for the purpose of working out this inequality. So if x is between 4 and 6, well, look, I've got the absolute value of x minus a is right here, the absolute value of x minus 5. My problem is the x plus 5. But since I know that x is between 4 and 6, that means I know what the biggest possible value for x plus 5 is, right? X plus 5's absolute value has to be less than 6 plus 5, which is 11, right? The biggest value for x is 6, so the biggest value I'm going to get for this absolute value is 6 plus 5. So that means that I can rewrite my inequality here and say, well, this is true when the absolute value of x minus 5 times 11 is less than epsilon. And now I can divide by 11, and I get the absolute value of x minus 5 is less than epsilon over 11. Okay, so that means I can say choose delta equal to epsilon over 11, then if the absolute value of x minus 5 is less than delta, which is epsilon over 11, we will get that the absolute value of x squared minus 25 is less than epsilon. And so we showed that the limit as x goes to 5 of x squared is 25. All right, so that's pretty much as tough as it could possibly get in this course. You know, this is a Calculus 1 course. Oftentimes in a real analysis course or intermediate analysis course, you're going to deal with a lot more of these rigorous limit proofs for good reason. But I wouldn't expect students in a Calculus 1 course to deal with any functions more complicated than this. We really just want you to see and understand how the definition works, so that you know it's not magic, that there's actually something happening here that we're thinking really carefully about. Okay, so let's scroll on down to another example here. So this is example 7. Now, example 7 is a little different because here we want to show that a limit doesn't exist using the definition. So how can we do that? Well, typically the way that we will show a limit doesn't exist is by starting with the assumption that it does exist, and showing that if we make that assumption, we're going to reach some absurdity, right? So we call this a proof by contradiction. So let's try it out. Let's assume this limit exists and the limit is equal to some number L. Then, for any epsilon greater than 0, there is a delta greater than 0 such that the absolute value of x minus 0, because that's our a in this case, being less than delta would imply that the absolute value of 1 over x minus L is less than epsilon. Okay, but if that's true, let's see what would happen. If the absolute value of 1 over x minus L is less than epsilon, that means 1 over x minus L is between epsilon and negative epsilon, which would imply that 1 over x is between L minus epsilon and L plus epsilon. And if the absolute value of x minus 0, which is x, is less than 1 over L plus 2 epsilon, what would happen? Okay, and I'll explain why I picked that number in just a moment. So, but first, I want to explain what I'm doing here. So this is what I'm picking for delta. Okay, I'm picking a number for delta because I know that when x gets really small, that 1 over x gets really big, right? 1 divided by 1/2 is 2. 1 divided by 1/5 is 5, right? The smaller I make the denominator here, the bigger the actual number gets. And so what I want to show is that it actually doesn't matter how small delta is. If I pick small deltas, I'm going to get numbers here that are bigger than either of these bounds, in which case this inequality won't make sense. So why did I pick 1 over L plus 2 epsilon? Well, because I want, when I take the reciprocal, I want 1 over x to be bigger than L plus epsilon. Hopefully that makes sense. So in other words, since x is less than 1 over L plus 2 epsilon, that means that 1 over x is greater than L plus 2 epsilon, because when you take a reciprocal on an inequality, you flip that inequality around. And that would imply that 1 over x is certainly bigger than the L plus epsilon, right? I just wanted to pick something that guaranteed I was bigger than that L plus epsilon. Hence, our assumption was wrong. And the limit does not exist. Right. All we've shown here is that this inequality that we should get when applying the formal definition, that the absolute value of 1 over x minus L is less than epsilon, can't be true because this 1 over x can get bigger than any number that we would ever bound it by, right? So this limit isn't a thing. All right, let's move on. So now we're going to talk about a important theorem, the summation law for limits. Now we're going to go over the proof of this. I want to be clear, I wouldn't expect a student to be able to do this proof on their own, but I do want you to see it and try to understand the logic of it, because we are going to use these types of properties all the time to evaluate limits. So the summation law for limits says if both the limit as x approaches c of f of x and the limit as x approaches c of g of x exist, then the limit of the sum of f of x plus g of x is equal to the limit of f plus the limit of g, all of course occurring when x approaches c. So what this means is if I have a limit of the sum of two functions, I can always evaluate it, if those limits exist, by evaluating each limit separately first and adding the results together. Okay, so let's go through the proof here. So we will denote L sub f to be the limit as x approaches c of f, and L sub g to be the limit as x approaches c of g. And let epsilon greater than 0 be given. So we want to find a delta greater than 0 such that whenever the distance from x to c is between 0 and delta, then the distance of f plus g and L sub f plus L sub g, the distance between f and g and their limits, is less than epsilon. Now we know that since the first limit of f exists, then for some epsilon 1 greater than 0, there's a delta 1 greater than 0, such that the absolute value of x minus c being less than delta 1 implies the absolute value of f of x minus L sub f is less than epsilon 1. Whew! Literally, I just wrote the definition of the limit here, right? But we called it epsilon 1 and delta 1 to distinguish that this is just the epsilon and delta for the function f rather than the sum. Now, we're going to look at epsilon 2. Greater than 0. There is a delta delta 2 greater than 0, such that whenever the absolute value of x minus c is less than delta 2, then the absolute value of g of x minus L sub g is less than epsilon 2. In other words, we just restated the definition of the limit for g, but we used epsilon 2 and delta 2. So now what we're going to say is, well, since we're adding these two functions together, we're really going to think of epsilon 1 and epsilon 2 as half of epsilon, right? The epsilon that we're looking for the sum of the functions, we're just going to set each individual function's epsilon to be epsilon over 2. But we'll get different deltas, right? Even though we chose both epsilons to be epsilon over 2, the delta we get is going to be different because the two functions are shaped different, right? One function might be like this, and one function might be really steep, and so the range you get on the x values is going to look a lot different. So what we do is pick the minimum value for delta. So we pick the smaller of the two. We pick that guy, because if the one function has the accuracy we want there, and the other function has the accuracy we want here, right? If I pick the smaller x-axis distance, it's going to keep me within that accuracy for both functions. So if we pick the smaller, the minimum delta, then we'll get that the absolute value of f of x plus g of x minus L sub f plus L sub g is equal to, and now I rearrange this inequality, the absolute value of f minus LF plus g minus LG, and that is less than or equal to the absolute value of f minus LF plus the absolute value of g minus LG. Now, this inequality here seems kind of arbitrary, but it's not. If you think about a triangle, in fact, we call this the triangle inequality, and you think of the lengths of the sides as being like vectors, right? What this inequality says is that v1 plus v2 is always bigger than v3. Meaning, if I start at the starting point, the same starting point, and I go to the sum of the two vectors, I travel along both and go to my endpoint, but I do it directly, I travel less actual distance than if I take the scenic route. Right? So this is called the triangle inequality. And this is true in general for any absolute values, right? This absolute value of v1 plus v2 is less than the absolute value of v1 plus the absolute value of v2. Okay, and since each of those things are less than epsilon over 2, the sum, which sums up to be epsilon, we showed that for a given delta, or for a given epsilon, we can find a delta that makes that inequality true, and so the limit is the limit of LF plus LG. Okay, that's a little tricky. Try to think about that one a little bit. Hopefully it'll make some sense. But let's go ahead and roll on and actually apply this idea. So we're nearing the end. Not much left to do at this point. So we've got a limit. We know two values of two limits, right? So we've got the limit as x approaches 3 of sine of pi over x is the square root of 3 over 2. And limit as x approaches 3 of x squared minus 9 over x minus 3 is 6. Evaluate the limit of their sums. So the limit of their sums is the limit of each function added to each other. And we already know those limits, so I don't have to redo any work. It was given to me. So this is the square root of 3 over 2 plus 6. Now we're going to look at a summary of limit laws. Now all of these limit laws can be proven with epsilon-delta arguments, just like we did for the sum law. Now the next one, the difference law, is really the same thing as the sum law because that's just adding a negative number. So the proof for the sum law is sufficient to justify the difference law. Now the product law has a different proof. It's a little bit trickier. And we're not going to go over that one because if I did, we'd be here all day. Now we also have a constant multiple law. It says if you have the limit of a constant times g of x, you can move that constant in front. Now, if you think about it, if you look at the product law, except the function was a constant, the limit of a constant is just itself, right? So if I have, here's a number 5, and I say, hey, what's the limit as x approaches 3 of 5? Well, it's just 5 because the y value that's being approached is 5, right? So in general, the limit of a constant as x approaches a constant, or x approaches c of some constant k, is always that number k, right? So what I'm saying here is the product rule, if you assume the function was a constant, justifies the constant multiple rule. And lastly, we have a quotient rule. Now, quotients are just multiplying by a reciprocal. So this is equivalent to the product rule, except that we can't divide by 0. So the quotient rule that lets you split this on quotients only applies if the limit of the denominator function is not 0. Okay, let's take a look at one last example. The limit as x approaches 7 of f of x is 4, and the limit as x approaches 7 of g of x is negative 3. Use limit laws to evaluate the following limit. So I don't know what the individual functions are, so I can't plug in anything into functions or anything like that. A really common mistake students make is that they'll plug the number 4 and negative 3 in place of f and g. But remember, we don't know the values of f and g at these points, so you can't replace f and g directly with them. So we need to instead use our limit laws to rewrite these things. So the first thing I'll use is the difference law. And the next thing we'll do is use the constant multiple law that says I can move this constant multiple 5 in front of the limit and leave f of x inside. And I can move this constant multiple 2 in front of the limit and leave g of x inside. And so this gives me 5 times 4 minus 2 times negative 3, and those values I just got from the statement of the question. So that's 20 plus 6, which is 26. Okay, well that's everything. Thank you for watching.